A group of students are working outdoors to find the height of a tree in the school grounds. They choose a sunny day and measure the length of the shadow cast by the tree. They find it to be 14.2 meters. Michael, one of the students, stands near the tree. They measure his shadow and find it to be 2.9 meters. Michael has already had his height measured for the census at school questionnaire and knows that it is 171 centimeters. Draw two triangles to illustrate the measurements given above and show all the data clearly. So I'm showing Michael here in green, and his shadow is also in green. This green line has a length of 2.9 meters. His height is 171 centimeters. This is 1.71 meters. We just divide this by 100 because there are 100 centimeters in a meter. Now, because the sun is so far away, the rays of sunlight are more or less parallel. So this represents a ray of sunlight, and same here. So these two triangles are similar triangles. They're both right angled triangles. And this angle here is equal to this angle here. Now, this angle is the angle of elevation to the sun. So we can calculate it by looking at this triangle here. So I'll draw this triangle over here again. So this side is 2.9. The height is 1.71 meters. And we're interested in finding this angle. I'll call this angle A. That's the angle I've indicated with a dot here. So I'm just looking at this triangle. Well, in this right angle triangle, the side opposite angle A is 1.71 and the side adjacent to angle A is 2.9. So to find angle A, we have to bring in these two sides. So the ratio we are interested in here is the tan of angle A. That's the side opposite A, 1.71, divided by the side adjacent to A, which is 2.9. Now we could find A a different way. We could find the length of the hypotenuse by using Pythagoras' theorem. So we could calculate this distance here. And then we could use, say, the sine rule. We could say 1.71 over sine of A equals this distance divided by the sine of 90 degrees. So we have one angle in this triangle. But we'd have to get this distance using Pythagoras, and then we'd have to apply the sine rule. That's more work. It's easier to use one of the ratios for right angle triangles. So we have 1.71 divided by 2.9. And we want to get the inverse tan of this quantity. Now we need to round this to the nearest degree. So we look at the first decimal place. If it's 5 or more, we add 1 to this number. So this number is closer to 31 degrees than it is to 30 degrees. So we write 31 degrees down. So now we found that this angle is 31 degrees and this angle is equal to it. This line is parallel to this line because the sun is so far away. So these two angles are the same. Now we need to get the height of the tree. So I'll draw out this bigger triangle. It's a right angle triangle. The length of the shadow of the tree is 14.2. This angle is 31 degrees. So we want to find this side here. Now we could use the sine rule to do this problem. We could call the side we're looking for small a. We always call something we're looking for A. If it's a side, we use small a. If this is small a, then this angle is capital A. And then we'd have to get another side, which we have. We call it small b, and the angle opposite small b is capital B. And we can easily get capital B here because we have two of the angles. So we can add these two angles and take from 180 to find B. So we could use the sine rule, but I won't do that. I'll use ratios for right angle triangles. So we need to get this side here. I'll actually call it A, although don't confuse A with adjacent. We have to bring in this side because we're looking for it, and this side here because we're given this. So bring in the side you're looking for and the side that you're given. So what ratio will do that? Well, we want the side that's opposite A, and we want to bring in the side that's adjacent to A. So that's opposite over adjacent, so that's the tan. So tan of this angle equals A over 14.2, opposite over adjacent. So now we just multiply both sides of this equation by 14.2. Get the tan of 31 degrees first, well, on this calculator, and multiply this by 14.2. We want this to 2 decimal places, so I'll write down 8.53 meters. So this is a very useful procedure for finding the height of an object. If we know the height of some given object like this person, and we know the length of the person's shadow, well, it doesn't have to be a person, whatever, some pole or whatever, some object that's vertically positioned in the ground. If we know its height and we know the length of the shadow, we can use that information to work out the height of some other object like this tree, as long as we know the length of the shadow of the tree.